5.8, exponential growth and decay models. Pretty much the same thing as we did with compound interest, but today we're going to see it with populations, half-life, how those populations increase and decrease exponentially. What's nice with this is growth is continuous for populations. So we will be essentially using PERT. And it doesn't matter if it's population, cells, population of an organism, of people, of a city, population of bugs, or if it's cells that are growing or dying. We end up using pretty much just PERT, where we have our original amount, it's growing continuously, we have our constant rate, which is K, and then time. Again, I do not have my calculator, so I'm just going to make do by leaving the work here for you and then just talking through it. And if you do need me to work anything out, I can work it out in class for you tomorrow. So we have the size of a insect population that is given to us by an equation already. So that's nice. We don't have to come up with the equation. So determine the number of insects at day 0. So for t, we're just going to plug in 0 and 0.02 times 0 is 0. E to the 0 is 1. Anything to the 0 power is 1. So I just get 500. Now using the same situation, what is the growth rate of the insect population? Well, here I just rewrote the equation that they gave us. So my growth rate is the 0.02, change it to a percent, and it's 2%. And then the next one, what is the population after 10 days? You plug in 10 for t. Use your calculator. When will the insect population reach 800? So again, I'm using the formula that they gave us, and all I have to do now is plug in the 800 for the ending amount. That's A of t, or if you're looking at PERT, it's just A. So no fancy stuff here. I start by dividing by the 500. In my calculator, that gives me a nice 1.6. Since there's nothing after the 6, I can just write 1.6. Because I have an E, I need to remember that E and ln will cancel each other out. So I see the E, so I ln both sides. So I have the natural log of 1.6. I'm not going to use my calculator yet. And then I just need to divide by 0.02. So in my calculator, I would do the natural log of 1.6, hit equals, get the answer, and then divide by 0.02. So practice, make sure you get the 23.5. And then the last one, when will the population double? If I start with 500, doubling it makes 1,000, and then you go through the exact same process as D. Divide by 500, we get 2. Natural log both sides, so that way the E cancels. The natural log of 2 divided by 0.02. Again, practice using your calculator. Next example. So now we're looking at this from kind of a chemistry point of view, biological point of view. We have iodine 131. That is a radioactive material, and over time it decays. It will eliminate itself from our environment. And we have a nice, well, I don't know if I'd call it a nice formula, but it's done for you so you don't have to find it, where A sub 0 is your initial amount, and our A of t is the amount at the end of so many days. And we are assuming that the scientist has 100 grams of this radioactive material. What is the decay rate? Well, if I look at my formula, I have A of t equals A sub 0 e to the negative 0.087 t. Well, the value of t, that's your rate. So I move my decimal place 2 times, 1, 2, and I have negative 0.87%. Now, using that same formula, how much is left after 100 days? Now, remember, the scientist is starting with 100 grams of the substance. So I take the formula, I plug in 100 for my a sub 0. Now it's just using your calculator. So E and then caret, exponent, make sure you use parentheses, please. Make sure you use the negative button if your calculator has that and not the subtraction button. And then you have to multiply it by 100. Please practice. Make sure you get 45.7. When will there be 70 grams left? So I'm using the same formula again, where it's A of t equals a sub 0 e to the negative 0.087 t. We need to remember a sub 0 is 100. That's what the scientist originally has. And then we want to end with 70, which means now we're looking for t. So I have to start by dividing by 100. So I get 0.7. Then I must natural log both sides so that way my e cancels. And then I can divide by the negative 0.087 and I get 4.1 days. Practice in your calculator. And then in D, what is the half-life? Half-life is used when we are determining the age of material. We do this a lot with carbon dating, knowing how fast carbon is eliminated from organic material. We are going to use the same concept here with this radioactive material, and we are going to find the half-life, meaning if I have that 100 grams that the scientist has, how long will it take for half of it to go away? So half of 100 is 50, and then I go through that exact same process that we did in the last two problems. I have E, so I want to get rid of the E, so I ln both sides. So I have the natural log of 0.5. Whoops. I have the natural log of 0.5, and then I divide by negative 0.087, and I get 7.9 days, years, whatever this function was expressed in. Okay, last example. So express n as a function of t. You were given a situation that goes with 8. This is number 8 from your book, but I didn't write everything out. But this is still the PERT formula. This is still A equals PE to the RT. N is your starting amount. N of T is your ending amount. K is your rate. So the population decreased from 900,000 to 800,000. 900,000 is your start. 800,000 is your end. From 2003 to 2005. That means 2 years has passed. What will the population be in 2007? Well, I'm not given the rate. That's a big question I need to ask myself. What is the rate? Which means we need to find the rate first. So that's my step 1, find K. Don't forget K is the same as your rate. So I'm ending with 800,000. I'm starting with 900,000. And 2 years has passed. So my only variable left is K. So I divide by 900,000, which leaves me with 8 over 9 after all those zeros cancel, equals e to the 2k. Then I natural log both sides, so the e cancels. I'm left with the natural log of 8 over 9, and then I have to divide that by 2. Practice using your calculator. This is what you get for your rate. And it is decreasing, which makes sense that it's negative because we're going from 900,000 to 800,000. In your calculator, it's the natural log, parentheses 8 divided by 9, close the parentheses, and then divide by 2. If you don't use parentheses, you will get this wrong. Please be careful. Now, that's not even what the question was asking. The question was asking, what will the population be in 2007? In order to get that population, I needed the rate. So I now have the rate. I'm going to go back into my regular equation, A equals PE to the RT, where it started with 900,000 people. That was my start. I now have my rate, negative 0.0589. Now 4 years, let's talk about where that is coming from. In 2003, that's when there was 900,000 people. We want to know what is the population in 2007. From 2003 to 2007, 4 years have passed. So now it's just a matter of using your calculator. I have this circled because that's what you need to do first in your calculator if you struggle with your calculator. Otherwise, you should be good to just go 900,000 E, and then with the caret, parentheses, negative 0.0, that's an ugly 5589 times 4. And then make sure you get the 711,886. And I'm not going to do the last example. If you get it, great. If not, not a big deal. It's something that I've decided to not go over with you guys this year. Any questions, make sure you ask them tomorrow. If not, you'll be ready to do your classwork. If you're struggling with your calculator, I need you to make sure you ask me. If you are not going to ask for help, I'm going to assume that you are getting it. Otherwise, I will see you tomorrow.